Okay, folks, thanks for tuning in. My name is Matt Thomas, and you're listening to the USGS Landslide Hazards Seminar. This meeting is hosted by the USGS Landslide Hazards Program and co-organized with contributions from Stephen Slaughter and Jamie Kostelnik. For those of you that are new to this meeting, you have the ability to submit questions via the chat window or to use the raise your hand feature in combination with your microphone or video camera. We're going to wait until the end of today's presentation to take questions. So in the meantime, please just do your best to make sure your microphone is muted and your camera is off when you're not intending to speak. It's my pleasure to introduce David Cavagnaro today. Dave graduated from Dartmouth in 2017 with a bachelor's in earth sciences, having done some research in post-glacial landslides in Uganda. Then he also did some work on coastal geomorphology topics with the Maine Geological Surveys and water quality and erosion mitigation with the Friends of the Northern Lake Champlain group in Vermont. He's currently pursuing a PhD in geology at the University of Nevada, Reno, where he's being advised by Scott McCoy. His research focuses primarily on post-fire debris flow hazards in the Western U.S. Dave, thank you for joining us today. I'll go ahead and let you take it away.
Thanks a lot, Matt. Hi, everyone. Yeah, thanks for the great introduction. Really a pleasure to be able to share some of my work with you folks today. So yeah, today I'll be discussing the distribution of post-fire debris flows in relation to observed rainfall anomalies and climate. And I'll be providing some local and regional scale insights. And so, as Matt mentioned, this is a large portion of my PhD work here at UNR, but it wouldn't be possible without the collaborators that we've been working with, many folks at the USGS, at the California Geological Survey, University of Arizona, and many other organizations as well. So here's just an image of one of the many debris flows that we've seen through part of this work. This is the Santa Lucia debris flow event in Monterey County, California at the Dolan Fire burn scar. And this is a pretty typical type of debris flow that we've seen in a burned area. I'll be discussing more about the Dolan Fire in detail, but just to give you an idea of the type of landscapes we're working in. So just to introduce some of the motivation for why we're working on this problem, anthropogenic climate change has led to increased severity of wildfires in the Western US. And so as a result, the amount of recently burned area in the Western US is also increasing. And so here's a plot from Williams et al. Showing the amount of recently burned area over the past few decades. And you can see in certain parts of, this is limited to California here, but in certain parts of California, such as the Sierra Nevada, that exponential increase has been even more strong than for the state overall and for Southern California. And simultaneously with this increase in severe wildfire, the population living in close proximity to wildfire-prone areas is also increasing. And as many of you may know, after a fire is extinguished, the hazards emanating from a burned area may persist for months to years after the fire itself. And a wide range of flow types can be observed in these steep burned areas during rainfall events. And so these flow types can range from flash floods, landslides and landslide generated debris flows, and also runoff generated debris flows, which will be the focus of most of what I'll be presenting here. So this is an image that I'm sure many of you are familiar with from the Montecito debris flow event after the Thomas Fire, just showing the size and scale of how catastrophic these events can be. So with sufficient observational history in any given landscape, we can predict these post-fire debris flows and the triggering conditions for them using empirical modeling methods based on past observations. So this is especially powerful in areas with a long observational history of fire and post-fire debris flows, such as Southern California. However, as I've shown, severe wildfires rapidly expanding in the wetter climates of the Western US, such as the Sierra Nevada and Northern California, And there's much less long-term observational history of debris flows in these landscapes. So just to provide a little bit of context, here's an image from 2 different fires in the Northern Sierra, pretty close to Reno. And so the first in recent decades to cross the Sierra crest was the Dolan Fire in July 2021. And you can see a image of the severely burned area from the Dolan Fire. And the second in recent history to cross the Sierra crest was only a month later with the Dixie Fire in August 2021, about 100 kilometers north of there. And so as you can see, these fires are expanding into wetter climates and areas that have sparse observational history of post-fire debris flows. So we want to ask the question, how might debris flow activity vary across these areas, specifically across different climates in which fires can burn? So here I'm showing 3 images here from different fires in the southwestern US, the Station Fire in the San Gabriel Mountains of Southern California, the Tamarack Fire in the Northern Sierra in California and Nevada, and the Woodbury Fire in Arizona. And these fires all saw destructive debris flow activity after the fire, but they all have very different climates in which the fire actually burned. So one metric of climate that we can look at is the 1-year 15-minute rain intensity, meaning on the average of 1-year return interval, what is the maximum rain intensity that falls over a 15-minute period? And you can see that varies in just between these 3 fires from 18 to about 50 millimeters per hour. So fires and debris flows are burning across diverse hydroclimates in the Western US. And given that fact, can we look at if there's variation in post-fire debris flow initiation across this hydroclimate gradient, similar to some findings that have been shown in prior landslide literature, where there's a variation in landslide initiation conditions across climate? So that's the motivation for what I'll be presenting. I'll give a little outline of exactly what I'll go through here. So in part 1, I'll show you a regional analysis that we've been working on to look at debris flow initiation thresholds across climate in the Western US. And in part 2, I'll go to a more local scale where I look at variability in debris flow initiation within individual fires that burn diverse climates. And I'll show examples from some of the field work we've been doing. And then in part 3, I'll touch on some of the implications for debris flow prediction and research under the conditions of climate change. So part 1 for this regional analysis, we want to look at how debris flow initiation might vary across climate, but there's many different ways to define climate. So I'll focus in on some of the more specific metrics of climatology that we'll be investigating. So we can look at climate in terms of mean annual precipitation, meaning on average per year, how much rainfall or how much precipitation does an area receive. And you can see just in the southwestern US, about an order of magnitude variation in mean annual precipitation, ranging from less than 200 millimeters a year to well over 2 meters per year of mean annual precipitation in some areas. We can also look at climate in terms of how intensely that rainfall is delivered to the landscape. So as I touched on earlier, we can measure climate of the climatology of extreme rainfall in terms of the 1-year 15-minute rainfall intensity. So you can also see high variations in the 1-year 15-minute rainfall intensity across the southwestern US that don't necessarily follow the exact pattern of mean annual precipitation. So for example, you can see in parts of Arizona and New Mexico that receive relatively low mean annual precipitation. They do tend to receive more intense rainfall on a yearly basis. And this is important because it's been shown that a 1-year recurrence interval storm is capable of generating post-fire debris flows in many landscapes. And so in the context of how much this magnitude of this 1-year storm varies, it gives us motivation for investigating how post-fire debris flow initiation might vary across this climate gradient. So we can also invert this map of 1-year 15-minute rainfall intensity to show what the recurrence interval of any given storm intensity might be. And that even further highlights the differences in hydroclimate across the Western US. So in this case, we're showing a 25 millimeter an hour storm, which is the equivalent of 1 inch per hour or a 1/4 inch delivered over 15 minutes, as this is 15-minute rainfall intensity. You can see some parts of the southwestern US receive such an intensity about 8 times a year on average in terms of return interval, and some areas receive this intensity only once every 8 years on average in terms of the return interval. So on top of these 3 climate metrics, we can show where fires have burned and where post-fire debris flows have been observed. So in this map here, I'm showing fire history over approximately the last century, spanning a large range of this climate gradient of the Western US, and then also debris flow observations from these burned areas. And so in this case, the debris flow observations are colored by the data source, meaning that debris flow observations that have gone into training existing predictive models are shown in this dark blue here, mostly focused around Southern California. Debris flow predictions used in the testing of these models are shown in a light blue, and then new debris flow observations that have been recorded since these predictive models have been developed are shown in pink here. And this full set of debris flows is what we'll be analyzing further in the first part of this talk. So diving into this database of debris flow observations, this is based on the training and testing data sets for the existing USGS predictive model, and with updates from our work as well as others. And so each one of these debris flows corresponds to a location, a name and date of the fire, and also a peak 15-minute rainfall intensity delivered by the storm. And for each set of debris flow observations in the database, they correspond with either a 0 or 1 debris flow response. So in this case, we're not classifying by debris flow volume or magnitude. We're just investigating whether a debris flow occurred or not under a given storm condition. And so from this database of approximately 1,500 basin level observations, we use this receiver operating characteristic methodology to compute a fire level threshold for debris flow initiation. And so this is similar to some of the efforts that have been done on a regional level to compute regional thresholds, but we're using it to compute thresholds at individual fires. And so the way this ROC algorithm works is we're iterating through possible thresholds, in this case from 0 to 120 millimeters per hour. And at each possible threshold, we compute a threat score, which is based on the number of true positives, false positives, and false negatives resulting from that given threshold. And when we iterate through this, it turns out that the peak threat score corresponds with the value of the ROC threshold at that fire. So here's 2 examples, one from this fire in California and one from Arizona, showing on the x-axis the threshold in terms of 15-minute rain intensity, and on the y-axis is the threat score corresponding to that threshold. And so the best statistical estimate of the threshold at each fire is shown in blue line, the dark blue line here, where the peak of the threat score corresponds to that threshold. So we can, using each of these fire level thresholds, we can investigate how they might vary across this 1-year 15-minute climate gradient. And so first I'll show the ROC thresholds and how they correlate with the local 1-year 15-minute rain intensity. And there's a moderately strong correlation here. which indicates that in general, fires in more intense hydroclimates tend to require higher rainfall intensities for post-fire debris flow initiation. Now, of course, this ROC algorithm is an estimate of fire-wide thresholds based on the available observations and based on peak 15-minute rainfall intensity of any given storm. So it's not an exact measure of the actual triggering conditions of the debris flow. So we can look at if triggering intensities tell a similar story. So here's an example of various time series from the Buzzard Fire debris flow events. And in each of these plots, the rain intensity is plotted as a blue line, and the in-channel pressure as measured by a pressure transducer is plotted as a black line. And so debris flows are relatively easy to identify on a pressure transducer time series because it's a very sharp increase in pressure due to the steep surge front associated with a debris flow. And so in each of these plots, there's a red circle at the inferred time of debris flow initiation. And based on the time of debris flow initiation from these time series, we can look further into what was the actual rainfall intensity that triggered the event rather than purely looking at the debris flow or purely looking at the rainfall intensity at the peak of the storm. And so we can do the same exercise where we correlate triggering intensities with local climate. And although the sample size is small due to the labor-intensive process of installing these systems, we also see a similar positive association with local climate, where more intense hydroclimates generally require more intense rain for debris flow initiation. And this, to stress the importance of these triggering intensities, I think that is something that the community into the future will benefit from having more data on triggering intensities from in-channel measurements such as this. So from both ROC thresholds and triggering intensities, we see a moderately strong correlation with local climate. And so on both of these plots, I'm plotting the 1 year 15-minute rain intensity on the x-axis, but there's many other ways to measure the climatology of rain intensity. So we're using this Atlas 14 database from NOAA. And in this case, we're using the 1 year 15-minute rain intensity, but rain intensity can be measured over various return intervals, such as from 1 to 50 years, and various storm durations from 5 to 120 minutes in this case. So we can also investigate the correlation of these ROC thresholds and triggering intensities with each of these data products. So this forms basically a matrix of 36 different rainfall intensity climatology products to test. And then we can also add in this PRISM mean annual precipitation data set that I showed in the maps earlier. So this forms about 37 different metrics of climatology that we can test the correlation with. And so when I plot the R-squared value of ROC thresholds and triggering thresholds versus each of these data products, so in this case, the various intensity durations are plotted on the x-axis and the various return intervals are plotted on the y-axis, we see the peak in R-squared occurring with the 1 year 15-minute rain intensity. And I think this is an interesting finding for a couple reasons. First, it's been shown in the past that a 1 year return interval storm is capable of generating debris flows across the southwestern US. So the location of the peak correlation at the 1 year return interval storm, I think, is partial evidence of this sensitivity to relatively common rainfall. And then in terms of the intensity duration, you can see on both ROC and triggering intensities, the R-squared values tend to drop off quite a bit at longer period rainfall. And I think this might be evidence of the sensitivity of debris flows to longer period, just shorter period rainfall as compared with other processes such as landslides. So it could be possible that the mechanisms that might be driving this association are more sensitive to short period rainfall as well. And so this is an investigation of specific debris flow events in this database and associated rainfall conditions. But we can also investigate this in a way that doesn't require quantification of the triggering conditions or rainfall conditions of any single event. So if debris flow initiation is correlated with local hydroclimate, then we should see that signal in the distribution of debris flow observations across hydroclimates in the Western US. Specifically, if debris flow initiation requires more intense rainfall in more intense hydroclimates, the distribution of debris flow observations relative to overall burned area should be relatively uniform across the hydroclimates of the Western US. So to investigate this further, we built this 2D hydroclimate space. In this case, we're showing mean annual precipitation on the x-axis and 1 year 15-minute rain intensity on the y-axis. And so any location in our study area can plot as a point in this space. And so I've just showed a selection of cities and where they occur in this space. Places like Tucson have relatively low mean annual precipitation, but in terms of rain intensity, the 1 year rain intensity is relatively high. Places like Redding, California have much higher mean annual precipitation, but slightly lower rain intensity. And we can also show this at the overall Western US as a 2D kernel density estimate in this space. So that's just shown by the dark cloud in this space here, showing the overall density of the study area and where it falls in this hydroclimate space. So we can also look specifically at steep burned area and where it lives in this hydroclimate space. So in this case, the dark red cloud of kernel density here is showing the overall kernel density of steep burned area within the study area and where it occupies this climate space. And the debris flow observations, which I show in map D here, the debris flow observations also occupy specific positions in this 2D hydroclimate space. And so we can also collapse these into one-dimensional kernel density curves to show the distribution of burned area and debris flows across the mean annual precipitation gradient, which is shown in A1 here, and the gradient in 1 year 15-minute rain intensity shown in A2. So in general, you can see that fires and debris flows occur at slightly wetter mean annual precipitation than the overall Western US, which is shown as a dotted line in each of these subplots. And I think that might be a result of vegetation limitations in the super dry areas. Might also be a result of the fact that the steep areas are probably more heavily vegetated and might receive more precipitation overall. And so if we want to investigate how debris flows sample the overall burned area, the overall distribution of burned area, we can compute this spatial density of debris flows. So we'll separate debris flow observations and overall burned area into bins of 10 millimeters per hour rate, 1 year, 15-minute rain intensity. And in each bin, we can compute a spatial density, which is essentially the number of debris flow observations in that bin divided by the overall land area of steep burned area in that bin. And then so we can have two competing hypotheses with this analysis. First is that if there's no inherent variation in debris flow initiation across hydroclimate, then the spatial density of debris flows should scale with the annual exceedance interval of any given storm, meaning that In more intense hydroclimates, if the debris flow threshold does not vary with climate, then you would expect to see exponentially higher density of debris flows in those more intense hydroclimates due to any given storm being exceeded more often. So if we say there was a relatively constant 25 millimeter per hour threshold that did not vary with hydroclimate, that threshold would be exceeded exponentially more often in the wetter hydroclimates, meaning that this, and I think the spatial density of debris flows would reflect that. And the competing hypothesis with that is that if there is variation of debris flow initiation with hydroclimate, then the spatial density of debris flows should have a relatively weak correlation with climate, because in more intense hydroclimates, the threshold is not surpassed exponentially more often due to that threshold being higher. So here I'll just plot along this vertical axis here in plot B, the spatial density of debris flows that we would expect given a constant threshold that did not vary across climate. And you would see an exponential pattern in this spatial density, meaning that at more intense hydroclimates, a fixed threshold is exceeded exponentially more often. And so this is just using the points from the database as a sampling of various climate conditions to compute this annual exceedance interval. And so on top of this, we can plot the spatial density of debris flow observations that we actually observe and compute a correlation with local climate. We can see that there's a weak correlation between the spatial density of debris flows and hydroclimate, suggesting that in more intense hydroclimates, a more intense rainfall is required to initiate a debris flow. And so this is a workflow that is consistent with what we showed for individual analyses of debris flow observations from the existing database. But this is a sort of a workflow that doesn't require individual quantification of debris flow initiation conditions. And so I think this consistency highlights the fact that there might be climatic variation in debris flow initiation conditions. So in part 2 of this talk, we're going to look at the same concept, but on a more local scale, testing the influence of rainfall climatology on a local scale. And so this is a picture also from the Dolan Fire in California, Rattlesnake Creek debris flow event. You can see a beautiful levee on the left side there from a post-fire debris flow. And I'll be focusing a little more on this Dolan Fire and the individual events within it and how they might suggest the influence of rainfall climatology. So if thresholds are correlated with the one-year storm intensity on a regional level, then normalizing the observed rainfall by the magnitude of the one-year storm could help us predict where we might see debris flows within a burned area. So we can compute this rainfall anomaly value, which is essentially an observed rainfall normalized by the local climatology of rainfall intensity. So this has been done before in landslide studies. And so our computation of rainfall anomaly will be based on the observed peak intensity divided by the one-year return interval rain intensity. And our hypothesis is that debris flows should be largely absent in portions of a burned area that received a rainfall anomaly value of less than 1. So here's some prior findings from landslide studies in unburned areas that use rainfall anomaly. This is a paper by Odenmark et al. 2019, looking at landslides in Japan in resulting from a heavy rainfall caused by a typhoon. And so in this map that I'm showing here, which is a figure from Mark et al. 2019, there's the absolute rainfall value in the top figure and the location of landslide observations in the study area. And then there's the rainfall normalized by local climate, which is shown in the bottom map. And through statistical analyses, they found that the rainfall normalized by local climate is a better predictor of where landslides should occur than the absolute rainfall value. And so we want to see if we can apply these same principles to a post-fire debris flow event. So as I showed, this absolute rainfall versus rainfall anomaly is not quite as easy as one might think to actually test within a fire, because not every fire provides an ideal setting for comparing these two metrics. So many fires just have a low range in climatology, meaning that it's impossible to test the influence of climate within these fires because there's no variation in climate within the burned area. Fires can also have a high range in climatology and a high range in event rainfall. And in that case, it's difficult to isolate the influence of climate because it might just so happen that the high intensity rainfall happened in the more intense part of the more climatologically intense part of the burn scar. But it's also possible to have a high range in climatology within a burned area and a low range in event rainfall. And that would provide an ideal natural experiment for testing the influence of climate. So in this plot here, I'm just showing a selection of fires and the range of 1 year, 15-minute rain intensity burned within that fire on the x-axis, and then the range of peak rain intensity across that fire on the y-axis. And you can see most fires just don't span a very large climate gradient. And so the rainfall anomaly map wouldn't look too different from the map of absolute rainfall. You can see certain fires like the Thomas Fire associated with the Montecito debris flow events has a high range in climatology, but also a high range in storm rainfall. And in that case, the heavy rainfall happened at the climatologically more intense side of the fire. But then there are the rare case of fires such as the Dolan Fire in Central California that saw a relatively high range of climatology burned within the individual fire and a relatively low range of peak rainfall delivered to that fire. So the Dolan Fire provides an ideal natural experiment for testing the influence of climatology within an individual burn scar and an individual set of debris flow events. So just some more background on the Dolan Fire. It's located in Monterey County, just south of Big Sur, California, and it burned about 30 kilometers inland from the coast. So it stretched from the coast to a pretty remote area inland from there. And as a result of this steep climate gradient on the coast of California, the Dolan Fire burned a wide range of climatology, ranging from about 500 to 1,300 millimeters per year mean annual precipitation, and about 26 to 52 millimeters per hour in terms of 1 year, 15-minute rain intensity. So a large portion of the hydroclimate gradient represented within the southwestern US as a whole was burned within this single burn scar. And so the Dolan Fire was then subjected to widespread heavy rainfall during an atmospheric river event in January 2021, with a peak rain intensity ranging from about 30 to 50 millimeters per hour across the burn scar. And you can see the large spatial scale of this storm in the bottom right map here, where compared to a short, intense burst of rainfall, such as a thunderstorm, the rainfall was relatively spatially uniform across the burn perimeter from the Dolan Fire. And so this rain resulted in numerous debris flows and floods across the burn scar. So here's an example of some of the many debris flow events that we saw within this burn scar during our couple of fieldwork campaigns. This Cathedral Creek on the flowing into the coastal part of the burn scar. You can see that's actually matte below the log there for scale. And then in this South Nacimiento tributary, that's matte circled with the yellow circle here, just showing the inundated area from this debris flow from a relatively small basin. And the Santa Lucia Creek and Slick Rock Creek had some beautiful debris flow deposits as well. So through pre and post-event worldview imagery, as well as field validation, we were able to produce a segment level map of the response from this individual storm event. So in this case, the pink and red segments are experienced debris flows. The yellow segments experienced flash flood-like conditions, and everything else didn't experience any catastrophic flows beyond normal stream flow. And so you can see debris flows are scattered across the whole burn scar in many different locations. And so using a network of tipping bucket rain gauges and by interpolating this short period rainfall, similar to what's been done at the Thomas Fire, we were able to produce a map of the peak rain intensity from this storm. And unfortunately, radar was poor quality across much of this study area. The NOAA radar quality index showed that the radar data was not accurate across much of the study area due to the remoteness of the area and the steep topography. So we were lucky enough to have a relatively dense network of rain gauges at the fire. And you can see debris flows span across basically the full range of peak rain intensity. We can also do the rainfall anomaly calculation, as I showed earlier, just dividing that peak rainfall by the map of the 1-year rainfall climatology. And in this case, you can see debris flows are confined to the area above the 1.0 rainfall anomaly contour, meaning that debris flows were largely triggered in areas where the magnitude of the 1-year return interval storm was exceeded. And so to better visualize this difference between absolute rainfall and rainfall anomaly, we can project this information onto a 2D phase space with any location falling in this phase space, the x-axis representing the climatology of the 1-year 15-minute storm, and the y-axis representing the peak observed 15-minute rainfall intensity delivered to that location. So we can first plot the overall fire perimeter as a kernel density estimate in this space, showing the climatology across the fire and the rainfall delivered to any location in the fire. And in this case, we can draw a 1-to-1 line where anything falling above the 1-to-1 line saw rainfall exceeding the 1-year storm, and anything falling below the 1-to-1 line saw rainfall that did not exceed the 1-year storm. And you can see it splits the fire pretty evenly. There's plenty of area in the fire that did not see a 1-year storm, and there's plenty of area in the fire that saw over a 1-year storm. And now we can drape debris flow observations onto this space as red points here, just sized by the overall basin area. And you can see that while the overall Dolan Fire perimeter spans a large part of this space, the debris flows are largely confined to the area that saw greater than a 1-year storm. And it's important to note that any constant threshold that is not sensitive to climate should plot as a horizontal line in this space. And no matter where you draw this threshold, it doesn't delineate the debris flow locations as effectively as a climatologically sensitive threshold. And so this is result from one fire that provides a relatively good natural experiment for isolating the influence of climate. But we can also see what we've found at other fires and see if they show similar findings. So this is the Tamarack Fire, one fire that I'll be showing you. So we can look at these 3 fires, the Dixie Fire in Plumas County, California, the Tamarack Fire in Alpine County, and then the Thomas Fire down near Montecito. And so for the Dixie and Tamarack Fire, we'll be showing our own mapping results similar to the workflow from Dolan, where in the Thomas Fire, the California Geological Survey has already mapped debris flow locations at that point and processed rainfall data. So first we'll start at the Dixie Fire. In this case, I'm showing radar-based rainfall estimates as the radar quality index was high across the study area and lined up well with the existing gauges. So at the Dixie Fire, the debris flow events that we saw tend to occur at or above the 1.0 rainfall anomaly contour, similar to at Dolan. And these are two separate events that are about 50 kilometers apart. And they're both at or above the 1.0 storm intensity. At the Tamarack fire, we see similar result where all of the debris flows and the flash flooding is confined to an area that saw over a 1-year return interval storm. And at the Thomas fire, we see a similar pattern where there was much higher return interval rainfall here, but largely the debris flows were confined to the area that saw greater than a 1-year return interval storm. So we can just look at these three maps side by side, and from the location of the 1.0 rainfall anomaly contour, that suggests that producing these rainfall anomaly maps, especially at fires that burned diverse climatology, producing these rainfall anomaly maps might help guide rapid post-event rescue and reconnaissance efforts. In the case of the Tamarack fire, we made the map before going out into the field, and it turned out that all of the debris flows we saw were within this area delineated by rainfall anomaly. So I won't dwell too much on the mechanisms in this talk, but there are a lot of possible mechanisms for why this might occur, why this correlation of debris flow initiation with climate might occur. So it's known that fire perturbs various soil properties, such as hydraulic conductivity, unsaturated soil water retention, but fire doesn't reset every landscape to equal values. There are still a lot of properties inherited from the unburned soils. So you can see in these different plots of saturated conductivity and unsaturated soil water retention, the burned values are not all the same across the different study sites, but the perturbation relative to the unburned value is generally consistent across the fires. So if the soil properties prior to the fire were already evolved with local climate, we hypothesize that the fire doesn't completely wipe out that association, and it lowers the return interval of rainfall required for debris flow generation, but doesn't reset everything to a climatologically insensitive state. And so there are many other mechanisms to test that have been discussed in prior work, such as vegetation effects, antecedent moisture, even drainage morphology, and how they're correlated with local climate. And so many of these mechanisms might be helping to drive the association of debris flow initiation with climate that we're finding. And so just to finish up with some implications of some of these findings under the context of climate change. This is an image from the Guernsey Creek event at Dixie Fire, which is in a relatively wet climate compared to most of the burned areas that we've historically seen, and in a very large fire also. So fires are getting larger and more severe, as has been shown in the past. And they're also burning into climatologically wetter areas. And as a result of this, individual fires are burning across multiple climate zones. And this might impact the utility of formulating a fire-wide threshold for early warning purposes if the fire itself has burned across multiple climate zones. So one quick analysis we did using the fire perimeters that I showed in the prior maps towards the beginning of this talk is we looked at for any given year, which fire burned the largest range of climatology that year, and plotted the range in 1-year 15-minute rain intensity, as well as the range in mean annual precipitation from that fire. And due to this increase in fire size, fire severity, and climatology in which fires are burning, it turns out that the peak range of hydroclimatology burned within an individual fire has really increased quite a lot in the last few decades, just due to this increasing size of fires. So since about 1980, the the peak intra-fire range of 1 year 15-minute rain intensity has approximately doubled, and the peak intra-fire range in mean annual precipitation has almost tripled since 1980, just due to the larger size and climatological conditions of some of these mega fires. And so as a result, formulating a threshold for an individual fire might not be appropriate in some of these large fires, such as the Dixie Fire that burned many different climate zones. And the other impact of climate change that's relevant here is that climatologically extreme rainfall is becoming more common with climate change. So despite trends towards less rainfall overall per year with climate change in many areas, the actual peak intensity of a given storm might be increasing. So in this case, I'm showing a picture from the Tamarack Fire, which was triggered by monsoon rainfall, more akin to something that you might see in Arizona on a yearly basis, not a thunderstorm, just a very strong monsoon, or not an isolated thunderstorm, just a strong monsoon rainfall that was abnormally strong for that area at that time of year. So I see an opportunity to test this further just using existing climatology maps and various predictions from circulation models to highlight hotspots where debris flow activity might be increasing disproportionately strongly in the future. So just to wrap up with some conclusions, we've shown some of our work from a regional scale analysis looking at fire level ROC based and triggering thresholds, and show that they tend to vary with the climatology of the local 1 year 15-minute storm. We've also shown a similar pattern at the local level at a few different fires, where the post-fire debris flows tend to occur in areas where the 1 year 15-minute rain intensity has been exceeded. And lastly, we've shown a little preliminary work into showing how these trends may help us understand and predict post-fire debris flow activity as climate change pushes severe wildfire into wetter climates and subjects burned landscapes to more extreme rainfall. So I just want to acknowledge some of our partners with this work at UNR, at USGS, at California Geological Survey, at the University of Arizona, UC Santa Cruz, and the University of California Natural Reserve System, as well as various forests of the U.S. Forest Service. And so with that, it's been a pleasure to present some of my work, leave you with some photos of various field sites, and as well as my email address. I'm always happy to chat more about this, and I hope we have some time for questions. Yeah, I'm happy to hear any questions that anyone has.